Welcome back, Science 9. Today we are going to go through some of those science log activities that I assigned you from chapter 1.2, current, potential difference, which is using amp for current and voltage for potential difference. So science log activity number 1 was asking, can you explain what the electrical energy is? Even though there are some different forms of answer can come out in here, but I think when it comes to grade 9 level, electric energy can be explained by energy carried by electrons. And I want to say this energy can be transformed into different type of energy That's what I want to put. When I mean by transform into different type of energy, I want you to think that electric fan, so that means electric energy will convert it into mechanical energy because fan has motor and motor rotate so that it generate wind, air current in that situation. This can be one of the example. The key thing is energy is carried by electrons. You can elaborate a little bit more by saying it has high potential to low potential, that we carry more energy, but I believe that goes a little bit more detailed than what you guys think. So let's go with second science log question. How does current electricity, which I'm gonna use red color, different from static electricity, which I'm gonna use indigo color? The difference is quite distinct actually. Current electricity, first of all, need source like battery and complete circuit, aka using wire, those kind of things. The current electricity require these two because they constantly let electrons flow. Do you guys remember the direction? Was it negative to positive or positive to negative? I'm not talking conventional one. It's always negative to positive end. This is a unique property of current electricity. Just like the word current mentioned over here, it has to flow all the time. And in order to make it flow, we need source and some kind of conductible wire that complete the circuit. If there is any gap, if there is any damage, we cannot. On the other hand, static electricity is once electron jump from one object to another, I like to say, through what should I say? Through rubbing or friction, comma. Once electron jump from one object to another, the charge stays. What I mean by that is, I mentioned to you using an example. We have human, we have a balloon. Let's say electron jump from balloon to human hair. Then that electron stays there and positively charged balloon, that polar property stays there. So that's the differences. No flow. The third one asks you to answer the question, how would you describe voltage? And we need to explain some analogy. First of all, let's define voltage. Voltage is unit to describe unit used to describe potential difference. Now we need to use analogy to explain what this potential difference is. You can use an example of dam. You can use example of water pressure in the hose or dam, something like that. List can go on. I'm gonna use both of them at one point. So for example, imagine I have dam number 1, dam number 2, and you have water, and so as water on the top with the gate. Now let's think about it. Which one will have or produce more energy? I like to say dam number 1 will have more energy generated because of high potential difference in this case. Different potential difference, if I use analogy, it can be the height difference. I'm going to call it H1, dam number 2, H2. Which height is, well, more longer distance? I like to say height number 1. And how does that produce more energy? Is because once the water is released and it's traveled down, 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 it's going to rotate the turbine inside of the dam 1 more than dam 2. So that can be a bit of a description using the analogy. High potential difference means high energy will be produced. Science log activity number 4 asks you to describe the difference between current and voltage. So I'm going to use a bit of analogy from here again, but current I'm going to use blue, voltage I'm going to use purple. Current first. Current is how much electron flows. So I like to say current is equal to flow rate of electrons. That's a one difference. And also unit can be another difference. We use amp. Versus voltage, talking about how much electrons available from one end to another end and that difference. So for instance, if I think about battery, negative M and positive N, and imagine this is connected like that. Now I want you to look at this area, negative end area. We have more electrons, thus it has a negative terminal at one end. Positive, on the other hand, we have absence of electrons. So because of these two, if you think about the difference between one end to another end, it can create quite a bit of a difference in terms of electron number. I should say different electron numbers. And that create energy. It works like a water differences in the different height and how that create energy, something like that. Voltage is possible measurement of potential energy due to the difference of electron number, if you will. Science log activity number 5 is more of a scenario question, so I'm going to highlight a few things. Assuming you're working in a farm environment and you require a high current battery to start a large tractor. While shopping for this battery, should you be more concerned about the voltage level or amp? I like to put a little emphasis in this case to amp, because let's think about it logically. You need high current battery. That means equal to you require high current carrying battery, if you think about. Not about potential energy or potential difference. That means in unit situation, current, we need high amp requiring battery or having battery. Therefore, I like to say you should be more concerned about the amp in this situation rather than the voltage. Science log activity number 6 is quite important because you need to describe how electricity gets from the generator station or power plant to your home, technically some kind of appliance, let's say blender in your kitchen, those kind of thing. So let's make a little chart in here. So we have a generating plant. Know the fact that generating plant have some kind of energy conversion. If you're talking about water dam, gravitational potential energy to electric energy. So, electric energy. Something like that. If you think about fossil fuel, combustion, heat energy to electric energy. Now, here's the thing though. Once that happens, you will notice that a lot of voltage, high potential energy carrying electric energy will be the result, isn't it? Which is quite dangerous. So, we need a help of transformer to bring the energy down, bring the voltage down to our safe level. Then this is carried by wire outside of the houses, or sometimes you see in the highway, you know, remember the wooden pole and then drum barrel looking thing, which is a transformer and an electron carried by that. Then we're gonna end it up getting our residence area, house if you will, and that's where we will connect our plug to appliances. Something like that. That is a generic picture of it. Alright, so what we are going to do now is we are going to go through some of those Unit D, Chapter 1.3, which is everything about electrical safety. I will not gonna push a lot for this chapter today because we were pretty much heavy on Chapter 1.1 and 1.2, so we're gonna go a little easy on this one. I really hope you never experience something called short circuits, but short circuit is when an electric circuit allows a current to travel along unintended path, and that's a key word, ladies and gentlemen. Oops. So, for example, I want you to look at the picture on the right side. Can you see that the wire crossover, and because of that, we have unintended interruption? And current, if you will. Because of this interruption, we basically facing some kind of spark and fire damage, those kind of thing. Without a safe, complete circuit, electricity will not gonna flow, it's rather gonna cause the damage. Therefore, if you like to consider or learn about short circuit, just consider that as an abnormal connection between two nodes. Two nodes, if you don't know what node is, which is okay, it's kind of like each of the end or intersection of the junction of the wire. You can think it in that way, or multiple path. But if the electron go to unintended path with no resistance, then that's when fire will happen. Let's talk about the danger of electric shock, especially when it comes to power line. I want you to look at the picture first. Did you notice that when it comes to the wire, it should have been connected from one end to another, but instead it have a little physical damage, and one of the end of the wire was dropped down. This area is, we call it energized area. It's gonna damage you, it's gonna shock you. It gets especially worse if we have rain, because water is a good conductor. About 10 meters around. You should not go anywhere nearby. So my advice is never approach a downed power line at all. Don't even go close by. We have something called electric field, and you have a hard time realizing because it's invisible field that affect things around. Any person coming in contact with the power line may create a short circuit because the current bypasses part of the normal circuits. What I mean by that is this. So imagine we have, hopefully not, but let's say grade 9 boy. Walk on that. Now, here's what happened. It's going to create a circuit. What I mean by that is, if we, actually, let me draw it more closer. Let's draw it as a person who contacted. Now, let's think about electron. Electron travel one end to another, but because you're having a physical contact or water that is around, moisture, anything like that, it's now creating a complete circuits that go around your body. We call it short circuits. So what happened is electrons can flow through your body. Generally, what happened after that is a paralysis because your nerves are damaged and you cannot use your muscles to escape. Talking about the electric shock damage, I'm going to tell you how small amount of electric current flow, if you will damage you. If you have ampere of 0.015 amp, that's already good enough to cause a painful shock to you, and it will make you lose muscle control. And think about it, 0.015 amp. If I convert it into milliamp, you just need to time it by 1,000. 15 milliamp is good enough to make you cause a painful shock. And current, if it's 0.1 amp, which if you again times by 1,000, 100 milliamp can actually kill you. So if you look at a little bit detailed situation about the effect of electric shock, here are the chart level. You start perceiving, there's an electric uncomfortness at 1 milliamp, and when it comes to threshold of your body, it's already 10 milliamp. Muscle will freeze in 50%, like LD50, how lethal dose kill 50% of population. This is like 50% of the population will have a muscle freeze, then there will be burning afterward. The 4 amp and over, look at the condition. Your heart will stop and organ and tissue will start burn. This is electrical damage. So our human body, yes, human body has some resistance, but not much at all. And if you're in a vehicle, and if you have some kind of power line that go through, I will tell you right now, stay in the car. Because car is a conductor. If you think about the electron movement, they will pass through the car and then go to the other area. If you open up the door, you are creating another short circuit that you can get damage. So if a down power line touches your vehicle, you're actually good. If you have to leave a vehicle jump, do not step out, because as soon as you step out, you're creating another circuit that will go through you. You are a conductor. Not the best conductor like metal, but you are still a conductor. Stepping to the ground would provide a path for the electricity to flow through you to the ground. The current does not flow well in insulator, but it does flow perfectly fine in conductors. We need to know those differences. Current does not flow insulators such as wood, rubber, plastic, and air. Those are the ones that you can think of two things. Number one, they're too tightly bonded in the atomic structure. Or number two, it doesn't let electron escape its atom. On the other hand, when it comes to conductors, think about metals, any metal, and also some other parts like ion solution. Seawater is a good example because seawater has sodium, chloride, magnesium, etc., etc. Anything that has ions can carry the electron. Today, I think I'm going to conclude my lesson in here. The next slide will show you the homework for today. So today's homework will be textbook page 295. I put 4 questions. There are no parts of it. Number 1, 5, 8, and 9. See you guys next time.